In this video, I will do a review of exponential functions, and I'm going to follow the plan that we developed in one of the previous videos called Precalculus Review. That is, we're going to first discuss the prerequisites um, that one has to master before um learning exponential functions, and then we will discuss the answers to the following prompts that are provided right over here. If you need to refresh your memory on what each of this stands for, please watch the calculus review video. So let's go ahead and get started with the discussion of the operations, expressions, and equations involved when working with exponential functions. When it comes to operations, naturally, one has to be able to exponentiate and compute, or rather evaluate, the following functions and the following expressions. Since we are not familiar with natural logarithm yet, let me exclude that one from over here. Now, in addition to this, one has to know the properties of exponents, which are listed here. There are 10 of them, and you should be able to recite all of them with not much effort. When it comes to expressions, again, we're working with exponential functions, so one has to be able to simplify exponential expressions. So there's a natural transition from arithmetic to precalculus in this regard. Exponential everything, exponential operation, exponential expression, and naturally one has to be able to solve exponential equations. General exponential equations are such that can be written in this form. And we solve this equation by using the property of exponents. That is, if the right side is positive, we just change the format of this equation from exponential to logarithmic. And by doing so, we may end up with a whole new equation whose solution set matches to the solution set of the original equation. However, if the right-hand side of this equation is less than or equal to 0, then such equation has no solutions, and you have to know that. Now that we finished the conversation about the prerequisites, let's move on and start talking about actually exponential functions. First, let's discuss the form. An exponential function can be written in this form, where we have some coefficient a times exponential expression b to the x plus c. We get the simplest exponential functions when a is equal to 1 and c is equal to 0, and graphs for different values of b, one being greater than 1 and the other one being between 0 and 1, shown on this slide. You can obtain those graphs by plugging in inputs into outputs. These outputs are not trivial. It's not that easy to find 0. I guess it is easy, actually. It's not that hard to square 0.3, right? So we should be able to produce these graphs relatively quickly. But regardless of whether b is greater than 1 or less than 1, we always get the following properties. We have the horizontal asymptote aligned with the x-axis in both cases, and then also in both cases we have the y-intercept y equals 1 right over here, right? So that's an interesting observation. Now, other graphs can be obtained from this parent graphs by applying linear transformations. However, when it comes to linear transformations and exponential functions, you will never need to apply horizontal compression, stretch, or shift, or flip, because whenever you have a linear transformation in the exponent, you can use the properties of exponents and simplify that expression into something that has only x in the exponent. Here you can see an example of such transformation, meaning that instead of, and honestly, ask yourself, would you rather graph this and handle like 4 different transformations, or you'd rather graph this that only has 2 transformations? I think the answer is obvious. Now, graphing other functions, I guess here we're not talking about natural exponential function. Graphing any other function of this form, we do utilize linear transformations, right? So we start with the parent function, then we stretch it, and then we move it. Remember that this one has an asymptote, so when you stretch it, only vertical, you have to be careful. So vertical shifts shift vertical asymptotes, horizontal shifts, I'm sorry, vertical shifts shift horizontal asymptotes. Did I say that? Yes, but don't shift vertical asymptotes. Horizontal shifts don't shift horizontal asymptotes, but do shift vertical asymptotes. Uh, and the same applies to stretches. Horizontal stretches do not stretch horizontal asymptotes, and vertical stretches do not stretch vertical asymptotes, but may stretch the location of the other asymptote. So again, it's not about memorization, but rather just understanding the effect of each transformation on all components of the graph. So a brief summary is use linear transformations. Now, here you can see the outcomes of graphing exponential functions depending on the combination of values a and b. So if b is greater than 1 and a is positive, this is what you get. If a is greater than 0 but b is between 0 and 1, this is what you get. If a is less than 0 but b is between 0 and 1, this is what you get. And if a is less than 0 and b is greater than 1, this is what you get. Now that you have the graph in front of you, you should be able to answer questions about the domain and the range. So domain is all real numbers because you can throw any number in the exponent, but the range is not all real numbers. You can see how the range is pretty much either the top or the bottom part of the horizontal asymptote. So you have to figure out the range, you have to know how to figure out the asymptote, but the asymptote is always at C. That's just the property of this graph, C being the vertical shift. So this table summarizes the ranges for different values of A in regards to being positive or negative. Now, when it comes to finding the intercepts, this is when you have to be able to evaluate the function at 0, or that's for to find the y-intercept, or to solve a simple exponential equation to find the x-intercept. Note that your graph may or may not have an x-intercept. It has no x-intercepts when the following inequality is true, and it has one x-intercept when the following inequality is true. Now, as I already stated, graphs of exponential functions do have horizontal asymptote at this level. So this is your vertical shift. The parent graph has it at 0, but plus c shifts it up if c is positive or down if c is negative. Exponential functions are continuous on the entire domain. And you should know that because there are no constraints on what to put in the exponent. Now, when it comes to monotonicity, the important fact is that all exponential functions are monotone, meaning that they always increase or always decrease. So they don't have that shifting behavior. They don't have turning points. And in general, the behavior can be described using the following chart. Again, it's not about memorization, but just understanding the effects of all of these components on the shape of the graph. Being monotone, all exponential functions are naturally one-to-one. That means they have inverses, and that means you have to be able to follow this procedure to find the inverse. Naturally, due to the relation between the operation of exponentiation and logarithm, inverse of an exponential function is always a logarithmic function, and vice versa. Now, when it comes to symmetry, exponential functions are not symmetric in any way. What's going on the left has nothing to do with what's going on the right. They actually have quite the opposite behavior, so no symmetry whatsoever. Special features are, again, it says right here, but even in English language, the word exponential growth is used as synonymous for very rapid growth. So you may not be a math whiz, but you may hear people saying, oh yeah, this is exponential growth, and everybody seems to understand what that means. So exponential functions are synonymous to rapid growth, and that makes them special, I guess. Let's talk about finding the equation. In general, the rule of thumb is you have to have as many points as the number of parameters. So in general, there are three parameters, A, B, and C. Frequently in applications, though, C is set equal to 0. And that means we frequently in applications will be given only two values, which is enough. We don't end up with linear equations here, system of linear equations, but we do end up, or are they linear again? No, they're not linear. We have a product here, right? So, but this system of two nonlinear equations is actually pretty straightforward. So straightforward that I can give you the general solution to this system. Now, your goal is not to memorize the solution, but just to understand the fact that we do have a system that you may need to solve, and solving it is actually straightforward and pretty doable. Now, when it comes to applications, exponential functions have many applications, and unlike linear functions, they used a lot to represent some processes where growth or decay is involved. But unlike linear approximations, we use exponential functions when we don't have constant rate of change. We use exponential functions when we have changing rate of change. So when your rate of change is proportional to the output, this is when we have exponential function. So again, we use exponential functions to model growth and decay processes, and we use this equation. Frequently C is equal to 0, but it doesn't have to be. And we interpret this, oh my God, we interpret this coefficient, not coefficient, the base of this exponential expression in the following way. So it's a percentage of growth, it involves the percentage of growth, right? So just like slope in the linear function tells you how fast something is growing, here's the same, in the same way it tells you that something is growing or decaying, but it tells you kind of in a different way. So we don't interpret it exactly the same way. So again, this is just a summary. The purpose of this review wasn't to give you all the details, but to kind of just brush up on your knowledge and give you the right direction in which you to move forward. So this concludes the review. And if you have questions about any of the slides or you may need more examples, please let me know in the comments below.